Welcome to Submodule 2 of 3 on deflection methods. In this section, we will continue with whipstocks, starting with open hull, and examine our operational considerations such as orientation. We will then conclude with jetting assemblies. As a revisit to cased hull whipstocks from the previous submodule, they are used to deflect the bit out of the casing by milling a window. The whipstock face, a concave spoon with transition steps, guides the pilot mill in the desired exit direction. Because the bit rotates clockwise, the pilot mill typically exits slightly to the right of the whipstock orientation by 10 degrees to 30 degrees. After the pilot mill, watermelon mills are run to smooth and gauge the exit window. The system consists of a bottom anchor, the whipstock body, the whip face with a scoop angle, the pilot mill, and upper and lower watermelon mills. Each component ensures that the casing window is clean, properly aligned, and smooth enough to allow subsequent drilling assemblies to pass through. Cased hull whipstocks are especially valuable in offshore sidetracks where precision is critical. They provide controlled exit depths and directions, reducing uncertainty compared to older cement plug methods. Their effectiveness relies heavily on orientation accuracy, anchor reliability, and mill quality. When properly executed, they create efficient, predictable exits that minimize risk and time in high-cost environments. The diagram on the right shows a schematic of a typical whipstock assembly step-up. At the bottom is an anchor, which is usually hydraulically activated. There are also mechanical anchors, which are activated by setting down weight on a packer or cement plug that has previously been set in place. This is connected to the whipstock, which is a concave spoon profile with the transition steps to guide the pilot mill. Above this is a mill bit, which is connected to the whipstock with a bolt that is sheared after the whipstock is anchored in place. It is connected to a lower watermelon mill. Both the bit and the lower mill are under gauge. This is then connected to an upper watermelon mill. The bit and lower mill are under gauge and the upper mill is full gauge. The upper mill finishes the exit to full gauge and dresses off the edges to make them smooth. On the right is a photo of a whipstock with the anchor at the bottom of the picture. The whip face is in gold along with the mill bit. An open-hole whipstock consists of a concave wedge or spoon that deflects the bit in the required direction. The tool is run below the BHA on a shear fixture, oriented to the desired azimuth, and then anchored into position. Anchoring can be achieved with hydraulically expanded anchors or mechanically by setting down on a cement plug or packer. Once set and drilling commences, normally with a motor or rotary steerable assembly, the concave face ensures that the bit is guided into a new trajectory at the planned inclination. While kicking off the whip face, the RPM needs to be limited until the stabilizers are fully inserted into the new hole, so as to prevent any unnecessary damage to either the whip face or the stabilizer. This method is best suited for medium to hard formations where mechanical guidance is required. One key consideration is the anchoring method. If poorly secured, the whipstock can shift, leading to inaccurate results. Another consideration is ensuring the whipstock's angle is appropriate for the desired build rate, typically in the range of 1 degree to 3 degrees. Open-hole whipstocks remain effective for certain sidetrack operations, particularly when other deflection methods fail. They demonstrate the principle of using mechanical wedges to redirect the bit, a simple yet robust solution that continues to find niche use in challenging conditions. This is a video clip showing the operation of the Trackmaster open-hole whipstock. The video starts with the top of the whipstock, which is connected to the bit via a bolt, which will later be sheared to release the bottom hole assembly and allow it to travel down the whipstock. The hydraulic hose is connected to the anchor. The directional driller initially orients the assembly until the whipstock is pointing in the desired direction for the kickoff. Once confirmed, the hydraulic anchor is set to lock the whipstock in place. This is done by applying pressure down the string from the surface. The BHA is worked up and down until the bolt connecting the bit to the whipstock is sheared. This also disconnected the hydraulic hose. Once the BHA is disconnected, it is free to rotate and the kickoff can begin, and the BHA works its way along the whip face while being deflected into the formation. Orientation is one of the most critical steps in using an open-hole whipstock. The Universal Bottom Hole Orienting Sub, or UBHO, aligns the survey tool, ensuring accurate tool face orientation. The operator typically uses a combination of gyros, an electromagnetic multi-shot EMS tool, or steering tools to achieve the desired direction. MWD tools can also be used, but only if the whipstock setting mechanism allows sufficient flow. Otherwise, electromagnetic signals must be transmitted. Once oriented, the whipstock face must remain stable while drilling begins. Otherwise, the azimuth may drift. Orientation is also sensitive to hole conditions. Cavings, washouts, or swelling can compromise tool stability. Frequent surveys are essential to confirm that the tool face has remained aligned during the process. Precision here saves costly rework later. A small misalignment in orientation can result in missing the geological target by hundreds of meters. The lesson is that orienting a whipstock is not just about setting it, it's about verifying stability and alignment throughout the operation. In directional drilling, the old rule applies: measure twice, drill once. When orienting a cased hole whipstock, the recommended direction depends on the hole angle. Below 5 degrees inclination, any azimuth can be selected without issue. Between 5 degrees and 30 degrees, orientation should be within plus or minus 60 degrees of the high side, while above 60 degrees, the safe range narrows to plus 30 to 45 degrees from the high side. A whipstock should never be set low side with its whip face facing down, as this causes the risk of the whip face falling into the center of the hole and preventing the pilot mill from passing. Open-hole whipstocks follow similar guidelines, but with limits reduced to about 2/3 of those values. Choosing the correct orientation is critical. Set it wrong, and the exit path may not align with the planned trajectory, forcing costly corrective action. Tools like gyros and MWD surveys are essential to confirm whipstock orientation before milling. Another consideration is hole condition. Washouts or ovality can cause the whipstock to seat imperfectly, leading to unintended azimuth changes. Best practice is to examine the survey listing for a tangent section and the formation logs for competent rock. This ensures the milled window and subsequent trajectory are aligned with geological and operational objectives. Jetting, sometimes called badgering, is a deflection method suited only to soft, unconsolidated formations. It involves using a large bit nozzle oriented in the desired direction. High-velocity mud flow, often exceeding 200 feet per second, erodes a pocket into the formation. Other nozzles are jetted at smaller sizes to prevent balling between cones. Once a pocket is spudded, typically 6 feet or so, the assembly is rotated to extend the deflection over about 60 feet. A survey is then taken to confirm the new azimuth. If the build is insufficient, additional spudding may be required. The biggest limitation of jetting is azimuth control. At higher inclinations, corrections become difficult, and hole stability is often compromised. Offshore, it can be used to a few hundred meters, but onshore, it is rarely practical. The BHA is stabilized with a long rotary build assembly, usually about 90 feet, to help maintain the desired curvature. While jetting is largely obsolete today, it represents a significant milestone in directional drilling history, demonstrating how fluid energy alone can be used to alter a well path. Question: can you think of an application where jetting would be a use case for today? I will give you a moment. An application would be top hole kickoffs in a very soft formation. Motors and rotary steerable tools struggle because the formation is washing away around the bit. Both systems need touch points to help leverage the deflection. With a jetting bit, this is an advantage. A second application, also in a soft formation, is for anti-collision. In situations where the trajectory is very close to an offset, a jetting assembly can be a suitable option. This is because the bit is not turning, so in the event of a collision, it would bounce off the casing. Let's revisit the learning objectives to consolidate what we've covered. First, you should now be able to list the 4 primary deflection methods: whipstock, jetting, steerable motors or turbo drills, and rotary steerable systems. Second, you should understand how each achieves controlled deflection, whether by mechanical wedge, hydraulic jetting, bent housing motors, or electronic pad and mandrel systems. Third, you should be able to state the advantages and limitations of each. Whipstocks are reliable in casing exits but inefficient in open hole, and jetting is limited but straightforward for soft formations. In the final part of this module, we will examine motors and rotary steerable systems. Thank you for watching this presentation on deflections. Please progress to the quiz.